Welcome to Python Labs. In this video, I'm going to cover classification methods in Python. So first, let's understand what is classification in data science and analytics. Now, classification by definition is the process of predicting a particular class, which we call as a dependent variable based on the predefined set of independent variables. In other words, if you have a data table, say for example like this, with rows and columns with all those feature attributes, the target, which is normally the last column, you want to predict something, then this one is basically what we call as dependent variable, and the remaining attributes are known as independent variable. So this is basically why we use classification, is to basically predict what for the given set of features, what is going to be the target class, what is going to be the target, the dependent variable results. So what we do is we basically we perform classification, but please note that we need to perform a number of pre-processing techniques in order to clean the data, or what we call as data engineering. And then we split the data set into training set, and the test set, a training set on which basically we train the model, and then we use the small piece of test, which is normally 10 to 20%, to test whether the model has been trained properly or not. And then we basically, the way we do is basically we apply different classification models, and then we basically compare the performances of the models, and then we validate and basically finalize which of the experimented models works best for the given data set. It is very important to know that different models work differently for the given data set. So at the end of the day, it all depends upon the piece of data set that you are working on. So the models will behave accordingly. So you need to find out which of the models for the given data set works best. Now, in this series of classification, the experiments or the tests that we are going to perform, we are going to apply a number of steps. Basically, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. So the first step, what we do is to import the needed libraries. Then we import the data, the step 2, and then we can shuffle the data set to avoid any bias, because sometimes you might be having the data set with the first few records in a particular way, and then the next few records in another way, and so on. And then we'll perform basically like different engineering steps and all those things. Let's go through one by one in this video. So step 1, importing the needed libraries, which is this. Basically here what we are doing is basically we are importing the most important libraries. This I have, by the way, please kindly watch my previous videos if you haven't watched, where I have already explained each of the code, most of the code that I'm going to cover in this particular video session as well. So here we are basically importing the needed libraries, primarily the mathematical NumPy and the matplot for library for the graphs, and for pandas for statistical data, seaborn again for some beautiful visualization, and we also use knn imputer for replacing some missing values. And then we also need to import the confusion matrix. I will explain each one of them as we go through. And then we basically need to import the sklearn metrics, which is basically the precision, recall, accuracy, F1 score, and so on. And I have already explained this before. We basically have these warnings at the beginning and the end, so that any errors are related to the importing the libraries. Those errors normally we do not need to worry about them, so we can simply ignore them. Now the first steps first. So again, as after we import the libraries, we read and view the data set. So we can read the data set with the pandas pd.read_csv, because I am reading a csv file here. And after that, you can also use these commands if you really want to see the general structure, or if you want to identify any missing values or null values. And you can also have this small piece of function you can print to identify all the missing values. So the next step is basically the optional step, which is sometimes you have the piece of data like this, say 1 to say 10,000 records, 10,000 records. Now what happens is the first few records might be in a particular way, the second piece of information might be in another way, and so on. That's why it is always better to shuffle around so that the data will not have any kind of bias. Now let me go through these first 1, 2, 3 steps in the code. So I have the code here. I'm basically having the first piece of code. I'm using Visual Studio Code, by the way, and I have written the code here. And in my classification, as you can see here, I have the classification file, which is this one, and I also have my data file opened already, which is clinical data. This data I have already explained quite a few times in my previous videos. So basically this is the piece of data that I will be basically using. As you can see in this data, there are a lot of inconsistencies. For example, here there are NA while numbers are missing, and here there is yes no, but here there is text. And if you can see like this, like for example, if you continue, you see there are NA which is not applicable or so on, and there are some columns with no headers, no text, and so on. And there's quite a lot of cleaning in this particular data set, but the purpose of this video is not about data cleaning. We have already discussed about data cleaning in my previous video, so I'm just going to ignore those steps. For now, we just import the data, we read the data, and once we read the data, we shuffle the data, as I told you, to avoid any kind of bias. And I have also provided some links, and this, by the way, this this is the link where you can find how this code has been, most of the code that I have utilized. I have already provided references so that you can go and read more if you want to. Now these are basically the part of the data engineering steps, which I have already explained in my previous video. And that's basically what I'm basically like, these are few 10 steps. Now what are these 10 steps? Removing unwanted features, because not all the features are important for classification. Removing any white spaces, and replacing any unwanted values with empty values, because we do not want to have a scenario where the values are are not relevant. And converting specific dimensions from objects to numeric data type, because we know that the numeric data types, well, at the end of the day, most of the classification models, they prefer to have the data in a numerical format, but not necessary most of the algorithms. And we convert the binary data into numeric, converting categorical data into numeric. How to convert all these things, I have already explained in my previous video. I will just quickly go through the code here, just to show you how it works. For example, df data frame dot drop, I'm dropping all those unwanted columns. Axis equals to 1 means at column level. And the next one is strip before and after white spaces. Sometimes we might see some kind of white spaces, and those white spaces before and after, it's not good. I have used, by the way, here lambda expression to to go through all the objects, because here I'm saying all the rows and all the columns. So it's a lambda expression to go through, loop through all the rows and the columns, and identify if there are any empty white spaces, then you basically strip them. And then you do the same thing for the column names. Sometimes the column names might have some kind of white spaces as well, which is not good. So we need to basically remove or strip out the white spaces from the column names as well. And then we replace the values such as na, no, n double back a, and so on, nil values, which are basically the human typo or some kind of error values or not applicable values. Those values, we just get rid of them in using the nan. Now what is nan? If you basically mouse over here, you can even you can find out the information. So anyway, now again I replace certain column, comma, empty, column space, these kind of things. And also I have replaced these kind of less than, greater than, and so on. I have already explained all these things in my previous video on how to clean the data. The purpose of this video is not to teach about not to go through these steps again, rather to focus on the classification. So the next step is converting specific object types to numeric, like for example data frame of weight. I have converted into float and so on, and then converting yes, no kind of values with the binary 1 or 0, and those are the ones. Converting gender columns, I have used for gender, I have used label encoder, label encoder. What is it? You can read here. Basically it can replace the values with 1 or 0 and so on. And then I have applied type of operation to just one type, and then I have applied some kind of data cleaning here. Again, yes, no, 1 or 0. We need to convert the features as int, and then classifying, I have done some kind of classification by looping through all the records for that particular column, and then I basically classified them so that I can do the prediction properly, because most of them, for example, this particular row, which is pathology, in this particular case, if you see here, pathology column, you see here, which is here, you see the pathology column, it's basically a collection of lot of different types of text here. If you notice, you see it's a huge kind of text. So I basically had to categorize each of these records into certain groups, basically like this, based on the text. And then we convert the features to categories, and then basically we use the column transformer using one hot code encoding. I have already explained this as well. One hot encoder, what is the purpose of one hot code encoder? I have already explained these things in my previous videos. And basically hold the newly created columns, because one hot code encoder, what it does is it creates new columns by splitting them, and those basically we merge those columns back to the data set. So these are basically the merging, and these are basically the part of the pre-processing steps. Again, there are additional more steps, which is called KNN imputation. Now, what is KNN imputation? I have already explained this in my previous video. Just to replace any kind of missing values, unknown values, how it will try to identify by finding the most closest nearest neighbors, and it will try to replace the null values with the most suitable value. Now please go through my previous videos on how to apply this KNN imputation, and apply feature scaling using min max scaler. This is again, what is a feature scaling? Now feature scaling is basically you see, you might have values in different variations. Some values from 0 to 1, some values maybe, like for example, the age might be in 0 to 100, whereas gender is male or female, for example 0 or 1. So these kind of variations, numbers are different, but we need to ensure all of them are age is in 0 to 100. It doesn't mean that this is bigger number means it has more value. No, they all are basically same. That's why to maintain the uniformity, we use the feature scaling using min max scaler. And when you apply min max scaler, the results of min max scaler, I think, if I'm not mistaken, this one, not this one, hang on, maybe this one, yeah, open results, open with CSV editor. You see, after applying that, you will basically, no, not this one, sorry, not this one, maybe this one, with CSV editor. And let me check here, min max. Once you apply the min max, it all the data would look like between between the scales. I'm just trying to find out for you, just bear with me for a second. So yes, this one, you see here all the values here, for example, irrespective of whether it is sex or age or weight or comorbidities, everything, all the values using the min max is basically between the values of 0 to 1, which means all the values, there is no bias. Otherwise, before, it used to be the weight of the person. If he is 100 kilos, that means if this is 100, it doesn't mean that 100 is bigger than if his age is only 18 years. So in order to maintain the consistency, that's what we use. Please go through my previous videos for knowing all these things. I have already done that in my previous videos. Now then, the final step is basically to split the data into X, which is independent variables, and the target, which is the dependent variables. Here I have again used the shorthand notation. Every column, what it means is, here it's basically all the rows. I did not specify from this particular record number to particular record number. And this one, what it means is the columns from this, all the columns minus one, of course, because when we are talking about independent variables, all the columns except the last column, which is the target. And when we are talking about the dependent, which is the target class, then it's just the last column. And because it is an array type where the values start from 0, that's why if you mention -1, whatever the values, -1, that is the last column. So once you have done all these preliminary steps, the next step, if I go back to the slides, so these are the performing the data engineering steps. You apply the KNN imputation, you apply the feature scaling, I already explained, min max scaler, and then you basically split the data into this kind of thing, split the data into the last column. This is basically all the columns here. All these columns are basically independent variables, which is this, everything except the last one, and this one is basically the last one, the last column. So once you split the data, then the next step or the good practice, what we need to do is to identify whether the target class, whatever the target we are trying to achieve, is the target is balanced or not. In this particular case, we have the values. For example, if I go back to the data set, for example, open with CSV editor, you see in my target class for the given attributes, my target here is whether there are any complications or not. This is my target. This is my target, whether the patient has complications, further complications. If yes, then we have to take certain decision. If no, then it's not necessary that we have to take any critical decisions. So, but now here yeses and nos, how many yeses and nos in my target? So that's basically, that really matters a lot. So that's basically what we are trying to say. If there are less yeses and there are too many nos, which means it may cause what we call as imbalance. So in order to solve this one, what we need to do is we need to balance the data. I will come to that point in a second. Now here first again we need to apply feature selection. Why feature selection? Because in all these columns, like for example, right from the beginning, all these columns, sex, age, weight, comorbidity, dates, length of stay, etc., etc., all these columns, not all these columns are actually giving enough information regarding our target, which is complicated or not complicated. So in order to identify which of these columns are most important columns that are directly impacting the target class, that is basically what we need to identify, and we do that with the help of feature selection. Now I already have another video basically on how to reduce the dimensionality or the dimensions, but this is basically one of the ways to reduce the number of dimensions. What we do is, if I go back to the code, you see here, this is basically showing graphically with the help of SNS Seaborn. We are displaying how many yeses and how many nos, which clearly says that the data target class doesn't have balance. Now after that, we split the data into training and testing. How you do that? Again, you use the sklearn, you import the library train test split, and then you basically categorize the data into 4: X train, X test, Y train, and Y test. Now you need to understand what each of them is. Now let me go through this slide here. You see here, let me, before I go into this one, let me erase this. So basically what it means is that, for example, you have your data set, right? Your data set is first split into independent variables, dependent variables. In other words, independent columns and the target column, target class. And then you also need to cut the data like this. What is this? This is basically what we call as training data, and this what we call as test data. We use the train data to train the model, whichever classification models you're using. And then once you have trained all those models, whichever classification, say classification model 1, 2, 3, 4, so on, and then you basically test whether these models are providing me exact results or not. So that's basically, normally what we do is 80% we split, 80-20 split. For example, 80% of the data we use for training and 20% of the data we use for testing. So once you split the data, and then X train, X test, Y train, and Y test, what we do is we apply the feature selection in order to identify the most important features. We don't want all the features. If you have, say for example, 30, 40, 50 features or columns, then there will be too many, and the experiment might be humongous as well. So we need to first identify the most important features. There are a number of ways to identify the features. There's another way called heat maps. There is a few other ways, but here in this particular case, what I have done is I have applied mutual info classification. Now, what is mutual info classification? You can just mouse over and you can read there. Basically, like this is estimating mutual information for the target class. Yani how much important these features are. So whatever the results are, you basically hold it into an array, and then you display the information with the highest to the lowest with the help of pandas.series. You display that array in the ascending order equals to false, which means show me from the highest to the lowest. Now the same thing you can basically display in the form of a graphical plot. For example, you can display here plot dot bar, which is a bar graph, and you are basically displaying the highest to the lowest. Now here is the code which is basically showing you feature selection, import, select k best features, select top n features, select k best features. This will display the top features, but while you are basically holding the top n. Now here k equals to 5. What it means is I'm interested in the only top 15 features or 15 columns, while I can ignore the rest. Now that is basically what I'm doing here, and I fit my training data and my training data x and y, which is basically what I display, and I hold the most important one while I ignore the other columns. I'm only holding the most important column. So what I'm trying to say here is you will be able to see the most important columns to the lowest important columns. I'm just interested in the top 15. Now it's up to you. You can set k equals to 10, which means the top 10 features, or k equals to 15, top 15 features. Totally up to you. So basically it all depends upon individual, but you will be able to see the data something like this. So that's basically what we are doing here. So feature selection. So once you have done the feature selection, you have identified that these are the most important features and I'm interested in. I ignore the remaining features and I'm just interested in these particular features. As I told you before, that I want to apply SMOTE. Why? SMOTE is basically applied for where are we here? You see here SMOTE. Let me go back to this code here. Apply SMOTE here. Once you see the SMOTE, why did we apply SMOTE? Because the data needs to be balanced. The data needs to be balanced. Why the data needs to be balanced? Because if you remember, I mentioned to you the data is imbalanced here. You see here the target. I'm talking about the target. The number of complication cases are very few, while the number of non-complications in this particular column, in the last column, which is this one, the number of non-complication cases are too many. So what we need to do is we need to balance these two. So we do that, we achieve that with the help of SMOTE technique. The SMOTE technique, which is this. So again, I have provided links here for locations where I have managed to get some beautiful piece of code. So this particular case of here we import SMOTE, and once we import SMOTE, and then we basically X train, Y train, we fit the resampling the data, and then we display. After here in this particular case, I have performed oversampling. It's totally up to you. You can apply oversampling or undersampling. It's totally up to you. But this is one of the ways, so that once you apply this what do you call SMOTE, then you rerun this code, which is basically this particular one. You will notice that the columns will be balanced. The target class will be balanced. So until now, what I have explained you is pretty much all part of the data engineering process. Now the most important thing. Now what I have got here is some amazing functions. You see here, these are some amazing functions that we can use as part of data classification, or we can reuse these functions on any data set, any piece of data set. That's something that I managed to find this through a lot of research, and they're really amazing. So let me go through one by one. So the first one, which is called k-fold cross validation. Now what is n-fold cross validation is, as we know that in the data set, we normally what we do is we split the data into training and testing data set, right? Now, with the help of n-fold cross validation or k-fold cross validation, what we can do is this piece of data, what we can do is first we split like this. Say, the say for example, we have 100 records, for example. Now, this particular first 20% and then the remaining 80%. And in the second round, we basically split the data. This is going to be our test data, while this and this is going to be our training data set. In the third round, this could be our test data, while this is our training data. So we are basically utilizing the entire data set by looping through again and again and again by using some small pieces of data set as testing, while the other piece of data is training. This is one of the best ways, especially if you want to, say for example, sometimes in our life, when we want to verify some kind of information, it is always better to verify among 2 people, 3 people, 4 people. So what here we are doing is we are basically verifying whether our model is working properly or not by using pretty much entire data set rather than just the last 20% records and so on. So that's how you do that. So basically, again, I have provided the entire code and also the links if I have extracted this from other sources. So this is in this particular case, k equals to 5. Again, you can specify k equals to 5 folds, 10 folds, 15 folds. It's totally up to you. So basically here we are cross validating and cross validating and verifying what is the accuracy, precision, recall, and f1 scores. So it will basically return all the what is the training accuracy, also the average accuracy or the mean training accuracy, and the same thing with the precision, what is the training precision scores as well as the average precision score. I will try to explain this after running. Please bear with me until the end of the video. So this is one of the functions basically for what we call as cross validation. The next function is for plotting a graph. Now, because we have the training data and the testing data, this is also extracted from another source, which is from the same source here. So what this one is doing here is to plot a graph showing the results of both training and test after applying the models, and after applying the n-fold cross validation. It's basically a graph displaying the graph with those kind of graphical features there. The next function, the common function that is really amazing, is called confusion matrix. Now, what is a confusion matrix? A confusion matrix in data science is basically kind of a table which defines the performance of a classification algorithm, how good or bad it is. Now, if you want me to show you one of the examples, this I have already explained to you, the plot graph, and this is basically what a confusion graphic look like. Anything like this, anything in this is basically good results. The other ones are true positives and false positives. Now you can have a 3 by 3 confusion matrix, you can have 4 by 4 confusion matrix. It's totally up to you, but whatever the results come like this, these are the best results. So basically here also we are trying to plot a confusion matrix. There's a common function. You can call this function pretty much to any data set that you are working for. It's basically looping through the records and trying to identify the true positives and the false negatives, true negative and false negative. This individual model statistics, you may ignore that one. Basically what it is to show you the precision, accuracy, f1 and recall scores at individual level. But in our case, for this particular video, we have utilized already this one, which is basically like performing and cross validation. So I'm going to ignore that. The last function, which is called AUC ROC curve. Now this curve is a graph that is extremely important because it shows the performance of the classification model, including all the thresholds. What are the thresholds? For example, the positive, true positive, false positive, and so on. It shows all those thresholds, and I will show you in a minute how it looks like. So if I go next, so that's the AUC ROC curve. So these are the functions that we have already identified. Now the next thing what we need to do is to directly apply the classification model. Now comes to the big part, the main part of this video. I will just go through one. You can apply the rest because the all of them are pretty much the same. It's just that you call different classification name, method name. That's basically what it is. Now, first one is logistic regression. Logistic regression is one of the popular classification model. Basically, the way you call it is using a sklearn linear model, import logistic regression. Once you call and then you classify, you fit the X train and the Y train. Once you have these values, then you try to apply the prediction. You predict the X test. You predict the X test. Why? Because you have already trained the data. Remember, in our case, what I told you, you will have basically whatever the piece of data set, the 80% of the data set you basically train. After that, you use for training, you use the trained data set. For testing, you use the test data set. Basically, that's basically what it is. Now, that's basically what it is. You see here, you pass the trained data, the entire trained data, and then you verify whether the values are, whether the test values are accurate or not. In other words, for example, the first one, the system predicted true while the actual value is 0. What it means is, in this particular column, for example, the last one, say for example the first one, here the complications is 0 while our model is predicting as 1, so which is not good. Basically, that's what it is. The next one, what we predicted and what is the actual value in the test is same, which is good, and so on. You can see there that how the values are basically predicting and testing, predicted value and the test value, predicted value and the test value, and so on. That's basically what it is. And then you can draw the confusion matrix, and you can plot or visualize the confusion matrix. What it means is that it has basically managed to find most of the 65 and 14, which are good values, which, as I told you, that anything in this kind of a shape are good values. The other ones are true, false positive, and false negative, so which is not good. Basically, what it means is what the system predicted and what is the actual value are not same. So that's basically what it is. Still, it is much better. Now, this is how you basically draw the confusion matrix, and you can perform the cross validation and view the cross validation. Print cross validation. Print cross validation. Now we are passing the linear regression classifier, X train, Y train, and we are passing 5 as the number of times we want to cross validate whether the values are correct or not correct. So again, print dictionary results line by line. You can print here like this, and then you plot the results. So what it means is, look at this. Because we have said 5 times I want to validate, so that is the first value, accuracy. This is the second accuracy, third accuracy, fourth accuracy, and fifth accuracy. And the average or the mean is 87.16. That is the average percentage of the accuracy. And the same thing applies for the precision, for the recall, F1 score, and so on. And this is basically how you can view the 5 times, because k equals to 5. That's why it's the first fold, second fold, third, fourth, and fifth fold. So 5 times, and then we take into consideration the average of all the things, be it accuracy, be it precision, be it F1 score, and so on. Now, the last one is basically, again, as I told you, it gives us the very good accuracy AUC ROC curve, which is showing you the overall performance, which is 0.94, which is 94%, which is really good percentage. So that is basically the overall percentage of the first linear regression, which is basically what we did here. Sorry, linear regression. So we basically call the linear regression model, we fit the model, we predicted the values, and then we compared what is predicted and what is actual, and then we applied the confusion matrix, and then we visualized through the confusion matrix, and then we applied n cross validation because we want to validate the the results again and again and again. Here we passed 5 means 5 times, 10 means 10 times, and so on, and we visualize these results. And then finally we overview the performance with the help of AUC ROC curve. So that's basically how you apply the classification model. I already explained the logistic regression. Now you can apply the same thing with the support vector machine, k nearest, naive decision. These are some popular classification models. You can do this, or you can apply any other model. Is totally up to you. Here I will just go through very quickly. See, this is the support vector machine. Again, in the support vector machine, I imported, you see here, I imported support vector machine. Sorry, so yeah, SVC, which is support vector classification model. And then I fit the model with my training data. And then I basically predicted with that, and I compared. This is basically comparing what is predicted and what is the test value, what is the actual value. So my system is predicting 1 while the actual value is 0, which is not good. What I predicted, what I got should be same, and so on. Once I do that one, and then I basically apply the confusion matrix on my SVM confusion matrix. And then once I got the results, I visualize the same thing with the help of support vector machine, what do you call, the confusion matrix. After I do that, I apply the n cross validation for the support vector machine this time, and then I pass n as 5, and then I visualize the result, and the results are again the same thing, 0.87, so on. I set k equals to 5, that's why 5 results and the average. And then I visualize the results, and then finally I apply the plot the ROC curve. And the same thing applies for the k nearest neighbor. Again, k nearest neighbor, this time k, import the k nearest neighbor library, and then I pass my training data, and then I predict the data with the help of test, and then I compare whether my training and testing is same, whether my predicted and my test is same or not. After that, again I basically apply the confusion matrix, and then I visualize the confusion matrix. After that, I basically apply the n cross validation for this knn classifier, and then I print the results. And then I plot the results. I print the results of everything, and then I plot the results, and finally I apply the ROC curve. And then the next one I applied is the Nye-based classifier. So Nye-based classifier, again there is a Gaussian NB Nye-based, and from there I basically fit my training data, and then I predicted for the test data, and then I compared my prediction with the actual test values. You see, most of the values are quite good. And then once I did that, I basically apply the confusion matrix for my Nye-based classifier data, and then I visualize the results in the Nye-based classifier, and then I basically apply n cross validation. Now n cross validation to ensure and then in the n cross validation I print the results and I visualize the results. So I print the results like this, n equals to 5, that's why 5 results, and then I visualize the results, and then I finally apply the ROC curve. So that is 0.97, which is a very good result. And then the last one I believe is the decision tree, and the decision tree I apply through the decision tree classifier, and then I fit for the training data, and I predict using the test data, and I compare my predicted values with the actual values. And then once I predict and compare the values, I apply the confusion matrix to identify what are the true positive, true negative, false positive, and false negative. And then I basically visualize using the confusion matrix, and once I visualize the confusion matrix, then I apply n cross validation, where I am printing the results as well as I am plotting the results. So the same thing here. Now what you can see here is basically like the results are really amazing here. Let's see, using the ROC curve. In the ROC curve 0.77, okay, 0.77, okay. So basically this is the ROC curve. And now once I have done all these different models, all the remaining models, the last step I need to do is to compare the performance all together, right? I want to compare all the values together, the the linear regression, SVM, KNN, Nye-based, decision tree, and so on. So I basically take into consideration only the mean values, because I am after the n, I have applied n cross validation. That's why I'm more interested in the mean values only. And once I have the mean values, I'm basically plotting the graph, and I'm displaying the results in the form of printing. You see here, basically I draw a chart. I try here, I'm taking into consideration only the precision, the accuracies. You can take into consideration other values such as recall, F1 measure, and so on. You can draw accordingly. It's totally up to you. So once I basically take into consideration only the mean training accuracy. Why it is mean training accuracy? Because the name, if you go into this one, like for example, if I control result, you see here, that's basically print cross validation. If I click again in this one, print cross validation, you see here, this is basically displaying me the mean train accuracy. That's like an ID name, okay, and that is basically holding this value, the mean value. and I go back all the way down, and so basically I take all the means of the accuracies of all the experimented models, and I create the bar graph, and I display the results. So this is how the results look like: accuracies of all the models and the basically the results. So as you can see, the clearly the decision tree is outperforming compared to all the other results. Decision tree accuracy is 100%, while other accuracies are 87, 92, 180, and so on. So that brings an end to this video. So what we learned from here is what we basically have, how to perform classification, what is classification model, and what are the different data engineering steps that are prerequisite before you apply the classification model. And once you have got the clean data and there are no bias, if there are bias, you need to remove those bias, and then you can apply different classification models. And after you have applied the classification models, after you have visualized different classification models, you can even evaluate and compare to identify which of these models is the best performing model. In this particular case, definitely it's a decision tree which is the best performing model. In your case, it might be completely different depending upon the data set that you are working. Thank you so much for listening.